article is very nice, very readable, even for undergraduates, with some hints of higher level math associated there. And there is also the other article. It's not actually not published yet, but there is it's an archive, and then it shows really the potential of the subject. I will mention maybe in the last slide some of the extensions to some higher brow mathematics. Okay, but we'll start very simple. Okay, so here is we take a very simple model of bicycling, the most primitive, embarrassingly primitive model of bicycling. So you see there's 3 positions of the bicycle, seen from above. There are 2 tracks. There is the B, the back wheel track, the interior. Let's see, does it work? Yes, this is the interior one, and there is the exterior one. Okay, and there's only one rule. Okay, there is the bicycle length, right? The distance between the center of the front wheel and the back wheel, it is constant, of course. Rigid bicycle. You know, mathematicians, of course, come up with all kind of crazy extensions, but we keep to the very down-to-earth real bicycle. Well, not so real. Actually, bicycle is much more complicated than that. The only thing that we take from bicycle is this condition written here. You see, in each moment, the back wheel cannot move, of course. So the back wheel is kind of the no skid condition, right? That the back wheel is not moving sideways, it's always moving along the direction. Let's say the center of the back wheel is moving along the direction that the back wheel is pointing. So this is called the no skid condition, no resbalar. ¿Sí? ¿Pregunta? Okay. I can't hear. If you're lucky, exactly. If you're not skidding, there's no oil or something. So this is called the no skid condition. You know, when you park a car, you are also limited exactly by this condition. You have to kind of always to adjust to this condition. That's the back wheel. The front wheel, because of the what do you call it in English? I forget. The one, the manobrio. See, because of this thing, you can adjust it. Handlebar, of course. Okay. Actually, I learned handlebar before I learned the Spanish word, so, but I forgot it. So, okay, here I show you some animation. I made some animations especially for this talk, so more animations than formulas. Okay, let's see if this works. So see, this is more simplified version. This is the back track. I will always put in red or orange, whatever color it's looked, and the front track is blue. Okay, here it goes. So you're riding along nicely. I don't show the front wheel and this handlebar or anything. It's kind of obvious from the picture, right? And you can see that we are always watching this no skid condition for the back wheel. Is it clear? This is very important. This is the definition of this, everything that's going on afterwards. And it's kind of amazing that you can get so much from this very simple model. Okay, I'll show you some other. Here's another one. This is more artistic bicycling. You see, well, sometimes, this is like in a circus, like sometimes the back goes backwards. You see, it switches direction. The front, see, as we see later, we need big bicycle for that compared to the front wheel track size, you see? And so there are cusps. The front wheel path is smooth always in our model, but the back wheel will have cusps. The cusps occur exactly when you're 90 degrees. Maybe, I don't know if I can stop it. I can do it better here. Okay, so when does it happen that you have a cusp? You see, well, let's go forward. You are going forward now, but now you have a cusp. Let me see. It's better here. Okay, here we are going here forward, and then there is a cusp. The cusp, anyway, I'm not good at controlling this so much. Afterwards, people want to play with this. I have lots of these toys. Okay, so that's the thing. Here's, it can be pretty complicated, huh? Look at that. Back, you go backward, forward. Okay, so this is a basic phenomenon that can happen. That the back wheel, the back wheel path, the red thing will have cusps, the semi-cubical cusp. You can look at it generically, and then that's where the bicycle direction, the back wheel kind of start going backwards. If you put an odometer on the back wheel, it will kind of go back. Right, it will sort of subtract from the length. We have to measure the length of the back wheel. We have to measure with a sign. Pretty complicated, huh? Let's see some other guys. Here's another one. This is one of my favorites. We'll come back to this later. You see what happens? You're just going in a circle. The front wheel going in a circle. How many times you go around the blue circle before you come back to your original position? Can anyone guess? Not 3, of course. 4. You go 4 times. The front. We say that the front path is a multiple circle, 4 times a circle. Okay, and then the back path closes up. All right. This has a remarkable property. I will speak in a moment about what I call the bicycle monodromy of a curve, and this has some remarkable, not so easy to come up with this thing. So, okay, so this is bicycling in a plane, huh? Then we move on. Hopefully, if I don't get stuck on these toys too much, I will move on to 3-dimensional bicycling. Here's there's a famous curve called the tractrix. It's probably 17th, 18th century object. This is also produced by bicycling, okay, the tractrix. Sometimes you can imagine so you're going backwards, the back wheel, and then you go forward. And you can see very clearly where the cusp is created exactly when the handlebar is forming 90 degrees with the bicycle. That's exactly the condition where a cusp is formed. All right, questions? Clear? This is the warm-up, okay? So now we start with, here's another, before this, there's an amusing puzzle, maybe some of you know. I kind of do it for the high school kids in the workshop. I show them. So you have this, the puzzle is like this, like Sherlock Holmes style puzzle. You have 2 paths, right? The tracks, bicycle wheel tracks left on the mud after the criminal is left or something like that, and you are the detective and you look at it and you have to say which way did the bicycle go. I mean, I don't know, one of the tracks is back wheel. I don't put colors here, I want to keep the puzzle. So one of them is back, red in my notation, and one of them is blue, I don't tell you which, and they're going in some direction, right? Was he getting to the crime scene, or was he escaping from the crime scene? You look at it, can you guess? I gave you enough information in the slides before to solve this puzzle, I claim. So can you? All right, let's analyze it together with your permission. So, it could be this way. I mean that this is the back track going this way. Obviously not. So look where is the front track should be here, not here. So obviously that's not the right option, right? There are like 4, front, back. Let's take another one. Could it be going this way? Because the same argument. It couldn't be. So we just eliminated the possibility that this is back. So this is not back. So this should be front, right? So let's go for the other guy. Could it be this way? Now I'm making this one the back track and trying. So it has to be, the bicycle has to be this way. You have to reach all the way to this other track, right? If you want to be, so let's ride along. But if I don't want to change the bicycle size along my ride, which I shouldn't ride. I'm assuming it's not a rubber bicycle, it's a metal bicycle. So this doesn't work. So let's go for the fourth and last possibility. I was unlucky of, so this is no. So let's try this way, right? Now, same, this is the back track, but now I'm going, you know, from south to north. Let's try along the way. Yeah, works, works, works. This is the one, all right? Now you can tell your friends and little brothers and sisters, show them a puzzle. All right. So this illustrates again the no-skid condition is a strong condition. Actually, if you take a pair of curves in a plane, almost never they satisfy. I mean, you check 4 possibilities, none of them is satisfied. So it's okay. Here's the theorem, the first theorem. It's an easy theorem. It tells you about the area swept by the bicycle is a very simple formula. Yeah, actually tells you that if the back wheel could stand still. Yes, and then it's an area swept by the bicycle, right? And the proof actually is very simple. You can make it into a proof. You sort of break up this yellow thing into small triangles, right? And then you just join them, just slide them together, and you can see that they make up a whole circle of this area. So this is a rather, it's amusing, but it's a rather simple result. Here I apply it. Actually, it doesn't have to close the curves, all right? We can. It's actually the right way to calculate, you know, without entering into complicated integrals, to calculate the area under the tractrix. See, why is it pi over 2? I take a bicycle of length 1. Yeah, because exactly the bicycle is sweeping, you know, half a circle. If you imagine, you know, the angle is changing by pi. So if you slide all these small triangles, you get pi over 2. So that's the correct, quick way without integrals to calculate the area under a tractrix. Okay? All right, if you didn't get it, never mind. We continue. Okay, here we start raising the, introducing some real mathematics. I mean, this was also nice mathematics before, but now we just higher level. So what do? We consider the following thing. We take kind of discriminatory actions. We give a privilege to the front track, right? We say that the front track, right? Usually we ride along the front path, right? You don't ride along the right. So that's it. But how do you ride along? You first have to put the bicycle, right? You put the bicycle, you orient it initially in some position, direction, right? It doesn't have to be tangent to the initial, and then you just ride along, right? Here, you ride along, here, and then your back wheel trace some, see, you see that this is tangent in the beginning, this red, and tangent in the end, and it was tangent all the way. I didn't put animation, but. And so you, from initial direction, this is the initial one, I get a final direction, right? I get a transformation, I get a circle map. You see, I get a circle map depending for each curve in the plane, closed curve in the plane in this case. Each closed, it doesn't have to be embedded, it can be immersed. A closed curve in the plane, I get a circle map, I pick a point, and I get from the initial position. It depends, of course, on the bicycle length. For different bicycle lengths, you get different circle maps. And from the initial position to the end position, right? So it's a map from the circle to the circle. That's the central object of this whole lecture, the bicycle monodromy, we call it, right? Of course, it's not, I denote the notation, I put it depending only on gamma and L, but it depends on, of course, on the initial point. I didn't put the initial point, but we know if you change the initial point, you just change by conjugation, all right? So it's well defined up to conjugation, this map, all right? But so all these concepts that we apply to it will be conjugation independent, okay? So that's the bicycle monodromy. And here's the theorem. The theorem was proved in the 90s. Somebody noticed it. It's very nice. So this bicycle map, this bicycle monodromy, this circle map is not arbitrary. It's what's so-called a Möbius transformation. Yeah, it's one of the most famous classical groups. And so we have to look in this, in this group. And I will now look at it. So here's the proof first. What is the proof? The proof is very simple. There are many ways to parameterize this circle of possible bicycle directions, right? So the best way is what's so-called a projective, put a projective coordinate, do kind of like strographic projection from one of the points on a line. On this line is like a P line, and then you write a differential equation that capture exactly this no-skid condition. It's pretty simple. I will not go through this now. It's a nice exercise. And you get an ODE, first order ODE. Tells you how you should reorient the bicycle along the curve, right, as you ride along, and so to keep this no-skid condition. And it is this differential equations. Of course, the bicycle length here. Here is this. This capture the gamma. Actually, you only need to know the direction and the velocity at each point. But the main thing to notice about this equation is not linear. It's quadratic, and this is what's so-called the Riccati equation. Riccati equation is well known. It's a kind of a projectivization of a linear equation, right? So it's flow. That's what we're looking at. Is by projectivizing linear transformation. So it's exactly the Möbius transformations. Okay, so this is the standard argument. Let's explore the consequences so it's easier to digest what it means. So Möbius transformations, these are maybe usually we see them in complex analysis course, right? With complex variables, but here everything is real. Okay, so yeah, this is P, A, B, C, D. This is called a Möbius transformation or fractional linear transformation, sometimes it is called. And what? So you know, you look for fixed points. Yeah, the first classification, rough classification of them is by the properties of fixed points. So the fixed point is like a quadratic equation. If you write an equation for a fixed point and it's over the real, so it may have no solution, one solution, two solutions. So so here are so I'm showing you, if you look at it in the real line, so it's very easy. The one kind of expansion, you know, it's one type of Möbius transformation. This is like has two fixed points. One is p equal to 0, another one is in infinity, right? So there are two fixed points, and then you have the one fixed point is translation. Only the point in infinity is fixed, and then you can have no fixed points. I write it like that, but it's actually better to look at it in the circle. It's just rotation. Yeah, rotations of the circle. These are elliptic ones, no fixed point. And there's another one, trivial. Just it's a group. It has an identity element. This turns out to be highly non-trivial, huh? to find curves with trivial monodromy. It can happen. Let's look at some examples. Huh? How does it look in real life, this thing? So we had curves around us all our life, but we never knew that have this interesting classification of these types. Yes? The parameter? Which parameter? Yeah, well, this A, B, C, D. Well, A, B, C, D by themselves don't have much meaning, because you have to make something which is conjugate invariant. So the main thing, the more important thing, is exactly what I'm saying. That number of fixed points and also this rotation angle. You have to give more geometric meaning, not A, B, C, D themselves. So that's what I'm doing now, right? I will show you what does. I mean, you can write hyperbolic, parabolic, and elliptic in terms of A, B, C, D, right? It's something like the trace of in terms of the trace is bigger or less than 2. You can write a formula in terms of A, B, C, D, but the geometric meaning of this formula is exactly what I'm writing, okay? That is the structure of fixed points, and then one fixed point is attractive, another one is repelling. Okay, so that's the geometric meaning of that. Let's see what it looks like on curves. What does it mean? So, Okay, so first, an obvious definition. I said that a closed curve is hyperbolic, parabolic, elliptic, if trivial, if it's monodromy, is like that. And of course, this is L-dependent. The bicycle monodromy of a curve depends, there's a parameter involved. Actually, we get infinitely many. For each parameter value, for each bicycle size, in a given curve, you have an adjective. It is hyperbolic with respect to bicycle riding with this length, elliptic, etc. Okay? Here's a hyperbolic, okay? So usually in real life bicycling, most curves are hyperbolic. Why? Because the bicycle is small, right, compared to the curve. If you're riding in a circus on a small stage, yes, you can be riding in some extremely small trajectories, but usually we ride along big trajectories, and that's the situation. You see, actually, so what does it mean, a fixed point? Let's think for a second. What does it mean, a fixed point of the monodromy? A fixed point monodromy means that the end orientation of the bicycle is equal to the beginning orientation, meaning that the back track is closed. Usually it doesn't have to close up. The front track closes up and you ride along, and if the end orientation of the bicycle is not the same as the initial one, then it doesn't close up the red curve, right? Fixed point of the monodromy means it does close up. So if you are hyperbolic, meaning there are two initial orientations for which the back track closes up. And here I'm showing you for an ellipse, all right? This was done with the Matemáticas, with the computer, and the computer found exactly what are this is one, starting here. If you start like this, you are close up. And there's another one. Now these two are pretty obvious because of the symmetries of the ellipse. I'll show you another one where it's not obvious at all. Here, arbitrary one. You see, this is one. It's another hyperbolic monodromy when the L is small enough. Okay. All right, so this is the hyperbolic monodromy. Okay? Questions? Did I answer your question from before, Claudio? Okay, good. Let's see another case. A parabolic monodromy. Parabolic monodromy is interesting. We'll see later. You see, you must have cusps in the rear wheel. In fact, the length is 0, meaning the algebraic length. We're going backwards as much as we're going forward with the back wheel. We will prove it in a moment with some nice formula. Okay? So that's parabolic situation. Elliptic one. Elliptic means, you see, I start in this position and it doesn't close up. I will end up with this position. You see? It doesn't close up. Here I'm making a little animation. I try other initial orientation and I always fail. Look, this shows you I'm sweeping through all the possible initial orientation, and for each one I'm looking at what is the resulting backtrack, and they never closes up. All right? It's actually, you can see that it's always kind of some positive, there's always some positive rotation. The end orientation is always positively rotated with respect to the initial orientation. That's exactly elliptic maybe transformation. It's not rotation, but it's conjugate to a rotation of the circle of orientations. Okay, and it's not an accident that the bicycle, you see, the bicycle is pretty big for this to happen, and it's not a coincidence. There's a theorem telling you that this happens if the bicycle is big, or rather the other way around. If the bicycle is small, say, but whether it's big, actually, it's not an if and only if. The bicycle is small, you'll have a hyperbolic. If it's big, there can be different things, but in particular, if you want it elliptic, the bicycle has to be big. Okay, move on. Trivial monodromy. Is it possible that you'll have trivial monodromy? Remember, this is the one from the beginning. So, can you have trivial monodromy? Meaning it doesn't matter how you start, okay, in which orientation you start writing, the back wheel will always close up. So this is a pretty simple answer to I mean, it's a simple question to answer. That yes, it's possible. It's very easy to come up, and that's how we came up with it. You take, for example, a circle. If you ride around the circle with a big bicycle, one loop, it's going to be a rotation. You can calculate it. It's okay. But if you take the correct bicycle length and you ride around, it will be a rotation by sort of a rational angle, a rational multiple of 2 pi. So if you ride enough times, it will close up. It doesn't matter how you start, because you see, because the monodromy is a rotation. Multiple of the rotation, the multiple of the correct rotation will be the identity. And that's exactly how we came up with this. So actually I start with this horizontal sort of initial orientation, but you can convince yourself very easily that if I just rotate it a little bit, the initial orientation, I can just rotate the whole picture. Because of the symmetry, it will also close up. So that's how it is. This is the bicycle monodromy of a 4 tuple, sort of 4 times a circle with the correct length. It will be trivial. Okay? And there is a spectrum of correct length for which it is trivial. And spectrum is interesting. All right? For a circle, we figure it out. For other ones, we don't know. But it's interesting situation of not interval. There's going to be some discrete. There's going to be some special values of bicycle length for which the monodromy is trivial. Okay, and here we see just one sort of value of this spectrum for a 4 tuple circle. All right, we analyzed carefully for all n tuple circles what's happening. I'll show you some diagrams further on. Okay, so that's trivial monodromy for a 4 tuple circle in this picture. Very pretty pictures you get from this simple question. Here's a theorem that I was referring to before. This was a conjecture for, I don't know, like 100 years. And it tells you exactly what I said before, that if you're riding with a small enough bicycle, you fix the curve. With a small enough bicycle, it will be hyperbolic. You will have 2 closed back tracks. And it tells you that it's the same thing with the circle. What happens in general is the same thing that happens in a circle. In a circle, you can analyze it carefully, and you can see that if the bicycle has the radius of the circle, it is parabolic. If it's smaller, you'll have 2 fixed points. If it's bigger, no fixed point. You cannot close up. And it tells you that it's a general situation. If you just take the area of the circle, happens in general. Okay. For convex curves. It's an elementary but highly non-trivial proof. A good project for the summer for undergraduates to read this proof of. This is the article I referenced in the beginning. So the first one. That's where they prove it, and then actually I think it's the first article that showed that the subject is worth attention. Right? There's some interesting theorems. Not just definitions and pictures. Okay, here's another theme that comes up, a very simple theme that actually rose in different guises during the years. You see, for some pairs of curves, I cannot answer this question, which way the bicycle went. I call them like ambiguous pairs. Why? Because I show you, for example, but very specially designed. A pair of circles, concentric circles, will have this. You see, I'm showing you. I don't know if you understand. See here, remember, this is the back, this is the front. So I can write this in this direction, orating. Yeah, this is the back track, this is the front track, and I can orient my bicycle like this, and then write clockwise. Yes, or. This same pair permits, if I just do the same exercise I did in the puzzle in the beginning, permits to do it the other way bicycle initially like. And counterclockwise, so I don't know which way the bicycle. I cannot deduce without any further help of arrows or something. I cannot deduce from the picture, from the static picture itself, what's going on. I mean, which way the bicycle went. Okay? So this is called, I call it ambiguous bicycle path. There are many other names depending. This turns out to be, this question came out, mathematically the same question came out in completely different contexts. Okay, there's one, I will not show this, but I just say it fast. There's a problem of Ulam, very famous, not solved yet, about floating bodies. Which bodies can float in equilibrium in water in arbitrary orientation. The sphere, of course, you take a uniform ball of some lighter than water material, some wood, and you can orient it any way you want, and it will always stay like that. All right? A two-dimensional version of this question, the three-dimensional version is not solved yet. We don't have any example other than a sphere. Yeah, the question if there's any other figures other than the uniform ball. So we don't know it in general, but in two-dimension we know it. And the question is exactly that. Right? It's interesting, and that. So, okay, going back to bicycling, forget about floating bodies. It's also another something about moving electrons in some magnetic field. There's another interesting interpretation of exactly the same mathematical question. Are there any other examples of ambiguous pairs other than two concentric circles? And the question is yes. Here is a physicist who investigated, actually is showing a, you can look up its website, and he's showing actually the three different formulations which I just mentioned. One is in bicycling, one is in floating body, and a third one is something with magnetic fields. And these are examples of figures. You have pairs. He doesn't use the code blue and red, but black and red. Close enough. So, and you can see, and the bicycle is green. And yeah, so in our language, okay, we'll just leave it like that. Okay, so this is fascinating. This actually is a whole lecture subject by itself. I will just now give you a quick reference to different subjects. I want to move on to three-dimension, but before that I have to show you some very central bicycling. Interesting transformation of bicycle curves, totally unexpected, but it is related to this business of ambiguous curves. So, okay, so here is a definition, probably the main sort of non-trivial. This monodromy thing, if you think about it, is pretty obvious, right? Whenever you have a bicycle, you have a ODE, you look at its flow, you look at it as a monodromy. This is not obvious definition. And we call it bicycle correspondence, but during the years it appeared, we now realize, we look back, Darboux, yeah, the expert on surface geometry, defined it, something background. Two curves, two closed curves, two blue curves, right? This is our prime. I mean, the two blue curves, two are in bicycle correspondence with parameter 2a. So it's what the picture shows, and the text says. What happened? I'm leaning here or something. Okay, so yes, I have an animation here showing you this. So they have this special property that they have like a common closed back path. You see? This red path serves as a red path for bike riding along both curves, the solid blue and the dotted blue. Okay, that's a definition. But you can reformulate it in different ways. You sort of, another formulation about it doesn't mention the red guy, yeah, just the two blue guys, the main characters. Another way to say it is that you fix a point on one of the curves, and you take kind of a stick. You take of length 2L, twice the bicycle length, and you sort of, you move it, you can see for two curves, typically you can move, as, 1 point on one curve, 1 point and just slide it along, right? But the condition that has to be satisfied is the following, that if you look at the midpoint of this kind of double bicycle, this stick of length 2L, the midpoint always moves tangent to the instantaneous position of this segment of length 2L, right? Because there's a wheel there's the common back wheel, and it cannot slide. So if you see, so it's always tangent. So anyway, you understand this bicycle correspondence business? This picture is supposed to help you. Okay, so that's definition. And now comes the theorem that justifies this definition. The theorem, the main theorem here, is that if you have two, okay, formulation, I mean, not so good. Luis scolded me yesterday. So imagine, forget about maybe, do I have a picture? No, another theorem, sorry. Okay, so if you have, it says the following, that you have two, suppose you have two curves, and they're in bicycle correspondence. Somehow, some bicycle length, maybe 2 kilometers, okay, bicycle length that connect this curve here and a curve on the other side of town. They're sort of related by this bicycle correspondence. Now it says that they have the same monodromies for any bike length, right? If I ride a bike of size 1 meter, around 1, and I look what is the monodromy, it's the same as the bicycle monodromy for the other one on the other side of town, riding a bicycle of length 1 or length 2 or whatever length. Okay, that's what it says. So you have two curves, gamma 1 and gamma 2, which are in some bicycle correspondence with some fixed bike length 2L. Then they have the same lambda by lambda, just I need another letter, okay? So then all their bicycle monodromies coincide. Of course, up to conjugates, you see, there's no meaning. Okay? The proof is extremely interesting, visual, but I cannot give it here, no time, okay? We're using some nice concept, we call it Darboux butterflies, and there's all kind of animations, but okay, so this is the main theorem that makes this magic of bicycle subject interesting, in my opinion. Okay, and there is a theorem, a very technical theorem that makes the whole thing, some commutative diagram. Okay, you bicycle correspond with one length and another length. You can do it in the other order. Very easy to swallow for mathematicians. But you have to be careful because they are not transformations. They are correspondences. You see, you cannot transform a curve by this bicycle correspondence because that typically, if there are any, there are two back tracks. Each one of them will produce you another one. So it's because it correspondence, not transformations. Okay, continue. All right, using this notion, so here our example. So now I take these multiple circles, this twice circle, 3 times, 4 times circle. Do you remember this guy? Without the dotted one. This is the one I showed you. 4 times circle. And here is now I do show the curve that you get by bicycle correspondence. And you see in each case that you see here, the dotted one is in bicycle correspondence with the solid one, well, multiple solid one. And so they have the same sort of spectrum. They have the same monodromy, although they look extremely different. And the main thing that using this construction and this Bianchi permutability, this commutativity, this is the easiest way to produce ambiguous curves. Right, to give a positive solution to this Ulam problem in the plane. Okay. All right, it's becoming technical. So I start going faster, huh? That's let's move on to 3D bicycling so you can relax. More pictures, no, less formula. So 3D bicycling, what does it mean? Okay, in Rn you can do the same thing. You can take a curve in Rn, right? So in R3, and you take a line segment and just make sure that you follow it one end following the curve, blue curve now in 3 space, and the other end tracing some red curve, right? But you make sure that the segment is always tangent to the red curve at each moment. So this may be like kite flying, right? You're dragging a kite, you're running around with a kite, and it's okay. So that's I call it 3D bicycling. Why? And you can play exactly the same game. So now you have, for example, in 3D, so there are a sphere, a 2-sphere of possible initial orientation, and ending up with so you have a map from a sphere to a sphere, in general from the n-1 sphere to the n-1 sphere, right? And actually a simple calculation shows that this map is also Möbius transformation. Yeah, you write the equation, you get kind of a Riccati equation. Easiest perhaps is to write, if you do it in three dimension, you write you put kind of a complex coordinate on this sphere. You think of it as a Riemann sphere, and you write a complex coordinate on it, the same thing in this stereographic projection, and you see that you get a complex Riccati equation. So it's okay. Again, it's a projectivization of a linear system, two-dimensional linear system, and so the monodromy is. See, here it have an interesting interpretation. Now the Möbius transformation of the 2-sphere, it's a great group. Okay, it has beautiful group, and it has many. It appears in different subjects of mathematics. Okay, here it's actually the conformal transformation of the sphere, right? We know this. There are also the holomorphic transformations of the sphere. Okay, and if you think of the sphere as the sphere in infinity of the hyperbolic 3 space, like say a hyperbolic 3 ball, so it's exactly what you get from the isometries of the 3 ball, right? That was the idea of many people, Thurston, that the transformal transformation of the sphere are actually what happens in infinity when you act inside the hyperbolic 3 space. This is also very relevant to our subject, but I will not pursue this. So ignore this point here. Okay. Now we play the following game. We take a curve in a plane. So it becomes kind of, I think, the most fun part. You take a curve in a plane. Let's look at ellipse with elliptic monodromy. I mean, there's no closed back tracks. Big bicycle. Remember that situation when I tried to look for a orientation with a big bicycle and I couldn't find? Okay, let's do that. But now I have another sort of degree of freedom. I can view of this plane is put in 3 space, so that I can allow initial orientations not planar. You see, a Möbius transformation from the sphere to the sphere always have 6 points. Yeah, a quadratic polynomial with complex coefficients always have a root. So there's always a fixed point. But a fixed point, I mean, this doesn't have to be horizontal orientation. What does it mean in bicycling? This is what it means. You have to lift the back wheel. Okay, if you lift the back wheel, and I got carried away looking for such pictures, I found even that. Okay, so here's an animation showing what's happening. Let's see if it works. No. This is Matemáticas. All right, so it's too big. Something happens when you switch from even smaller. Okay. All right, so we start with Give me a second. Okay, so here is a planar curve, the blue curve, and I'm looking at bicycling around with a short bicycle. So that's, as we've seen before, let's ride along, and I'm showing actually what the bicycle, actually you see there are cusps. If it's short enough, there'll be no cusps, but okay, so all right, so that's we have one. There's another one. Actually, it's hyperbolic, so there is another one. Here's the other one. Okay, there are two back curves. What time I started? In the end. 10:05. I have to finish in 5 minutes. You have 5 minutes. 5 minutes. Okay. All right, now I'll make the bicycle longer until I reach a parabolic and then beyond. Okay, so I make it longer, and here is parabolic, okay? Remember, zero length. Now beyond, what happens if I go beyond? There's still something happening, but what's happening? Well, we are not seeing because we have to look at 3 dimension. Oops. Aye. Okay, I think it doesn't like, I have to stop it. Oh, he's calculating, integrating numerically. Okay, you see what's happening? You see it, it's longer, the bicycle is longer, it doesn't fit. So it has to go to 3 dimensions, so you get, so here it, right? This is how you ride a bicycle around with a big bicycle, too big a bicycle. So you have to lift the back wheel. And that's how it looks like. If I make it longer, I have to lift even more. Okay. So that's the idea. Okay? Good. Back to presentation. I have to wrap up this thing. Shook? Yes. Good. Okay, so there's a formula that justifies several things that I said before. It's a nice formula. We call it Berry phase formula. It's a formula that the derivative of this, so it's a map from the sphere to the sphere, the monodromy, and if you have a closed backtrack, you have a fixed point, as I said before, and so you can calculate the derivative at this point. The derivative at this fixed point will tell you basically the conjugacy class of this monodromy. Okay, it's a simple exercise, linear algebra. So the formula tells you is this formula, right? It's a complex number, right? It's a derivative of a holomorphic map, so it's a complex number. There's a real part, and well, it's kind of polar decomposition. And in the formula, you see the interesting geometric ingredients. L, the capital L, is the length of the backtrack, but remember, the algebraic length, when we're going backwards, you have to subtract the length. You can have a non-trivial curve with 0 length. And this is an area. What is the area? Is that you can look at a bicycle, right? You move around and you just translate it like a Gauss map. You map it to the sphere, the bicycle direction. So it sweeps a curve, some closed curve, right, on the sphere, and it has an area inside that goes into this formula. So that's why we call it Berry phase formula, because usually they go like that. So we derive a consequence, you see? What happens if this applies in particular to planar curves? So if you have a planar curve, the area that you are sweeping, the R is, it's either nothing or a hemisphere, like 2 pi. So e to the I 2 pi is 0. So this whole thing dies, right? For planar thing, this e to the I a is 1. So, and then if you're parabolic, the derivative has to be 1. So this has to be 0. So the length has to be 0. So that explains exactly why we've seen for parabolic cases, you see these diamond shapes that they're kind of balanced. And also, you can, with this, you can count the number of cusps, and it's a nice application of this formula. Another application of this formula, so this is what I said. Another application of this formula is, you remember these circles, and we are multiple circles, and I look for this spectrum, this bicycle length for which it is, the monodromy is trivial. You can fuss around with equations, but it's immediate consequence of this Berry phase formula. Don't have time, so I will not show you, but it's very elementary. Okay, homework. All right, I do kind of very fast forward, and I show you. And what's the homework is? What the hell is going on here? Right? There is a circle. There's a multiple circle. I think it's a five-fold circle. I'd say it's a five-fold circle. Yeah, the picture repeats itself after the point here, the bottom goes around 5 times, and this is the curve that it generates. You know, this is kind of the 2L. This is the 2L. This edge on the bottom is generating this curve in bicycle correspondence with this five-fold circle. And then we apply this magic of this Bianchi permutability, which I didn't say much about. And then we get 3D curves in bicycle correspondence with these planar curves. And all these curves happily have the same monodromy up to conjugation. And there is this red curve, and I almost told you what's everything. But here is this is the object that makes this permutability works is this, we call it Darboux butterfly. And my time is over, so I leave you homework for the reader. And here's some further things I didn't mention. Using this formula of this Berry phase formula, you can make a bicycle, big bicycle, small curve, into an instrument, a planimeter. You can measure the area of curves, okay? Not very precise, but it's actually the most very simple to build. You know, planimeter before in museums, in science museums, you can see them, all kind of gadgets with balls and wheels and stuff. No, nothing of that. Just something that slides around and you can. Okay, actually the original interest, 19th century interest in this sort of mathematics here came out from this, people were looking for design of planimeters. This article I mentioned at the beginning from 2009 of Mark Levi and Sergei Tabachnikov explains this very nicely. Another, I just hinted about this subject, oops, in a moment. I hinted at this subject. There's a lot of hyperbolic geometry going on. There's another interpretation of this bicycling. You can think of it as describing the rolling of the hyperbolic. If in the plane, it's the hyperbolic disk. You roll it along the hyperbolic plane. Such things exist. Mathematicians, come up with everything. So, and if you want to describe this, the mathematical model for this rolling of hyperbolic plane or ball in 3 space on Euclidean space is the same thing. Is the same math. And but the most exciting thing, in my opinion, is this business coming from this bicycle correspondence. It's still a conjecture, what says here. There's the article of Sergei, which is this preprint I mentioned that was put up this year, explained this. There is a completely integrable system, infinite dimensional, integrable system hiding behind here. Right, we take a curve, I'd say it very quickly. You take a curve in 3 space, and you take one of these back curves, so you get a vector field, right? Well-defined periodic sort of vector field. There are 2 of them, typically. Vector field. This vector field, you use it to flow the curve. Yes? But now this vector field depends on the bicycle length. you can take a kind of a trivial series of this vector field in the bicycle length. In fact, the correct thing is to do the reciprocal of the bicycle length, doesn't matter. So you get a whole infinitely many vector fields, naturally defined, along every closed curve. These vector fields define the flow on a space of curves in 3 space, and the claim that this flow with the correct symplectic structure and everything is a completely integrable flow, and there are many good indications this is the case, and because there's a relation with a famous such curve evolution flow called the filament equations, a very old and classical subject now, and it seems like that the filament equation is nothing but riding a bicycle with imaginary length, something like that. In the formulas, you change L to I times L, and puff, magic you comes. So it seems that this is the situation. More details, look up the preprint of Sergei. It's fascinating. I don't understand half of it, but it's still fascinating. And now, in the end, this is it. And there's another one. There's a present. I will say, let's see. The music. You like music? All right, thank you. Feliz cumpleaños. Okay. All right. Okay, now serious. Let's get serious, huh? Ask good question. right?
Okay.
I think it's answering your question, no? With this,
Okay.
any front curve, smooth front curve is permissible, there's no restriction. Can be allowed. This will determine at most 2 back curves. Any front curve will determine.
Given that you already know that it's a front curve.
2.
If you already know that it's a front curve. But what if I give you a curve and I don't know if it's a front curve of anything?
For any curve, you declare it.
It's always
front. It's okay. It's a curve. You can write along any curve. No problem. You can write along any curve because an ODE. And you take the monodromy to ODE. It's a mixed transformation. And
The data that you put in is the back curve. Is that right? You put in the back curve and you take the tangents.
I thought it was the front curve with an initial orientation.
take the front curve. For any initial, that is an OD.
Oh,
so for
that's
any,
what I missed at the beginning.
for any, and then so but forget about the OD. So then you
Take a curve.
You take the front curve. Take your key with the bike.
I don't have
You
a
draw
back
a curve. You orient this bicycle, motor bicycle, initially in any way you want.
Yes.
You tell him ride it on.
Yes.
That's all. And then you trace. You put some red paint on the back wheel, and you trace this. What's the OD describing what
I
it is.
see. Okay. So any
It's very
curve.
easy to derive, and that's it.
Okay.
There's no restriction on the front wheel. On the back wheel curve, it's not usual thing, but you can also do the same thing. You take any curve you want, right? Clasps and all. You have to sort of orient, okay? Precise. That's the only thing that you have to do. Some choice. And so when you put a bicycle, you have to decide which way it's going. And you just take this tangent of fixed length.
Yes. Yes.
And look at the other point, what it leaves. This will be the
Thank you.
front curve corresponding to the straight.
Thank you.
There's no condition on this curve. That answer the question? Okay. If not, how can we
Any other questions?
excuse me? Linked. I mean the back. Yeah, of course. You can be linked. I don't have anything interesting to say about how the topology of the front and back in free space related to the monodromy, but technically it is great. You see, one of the things that we don't have is the three-dimensional Manzin conjecture. Remember this thing about the area? So maybe there's something that says, it's linked in the monodromy such and such, some global statement about the monodromy related to the global properties of the curve. That's the, see, the geometry is defined locally. Then you're looking for global